Welcome! In this calculus tutorial on differentiation, what we're going to do is look at curve sketching, and then after we do some curve sketching, we'll do some optimizations problems in finding maxima or minima, max and min problems. Okay, let's begin with question 1. Now, question 1 through 4 are about sketching a simple quadratic curve or parabola. But it's scripted, so it's 1 through 4 scripted in. So first we find where x is increasing and decreasing in question 1. So let's begin. Okay, so we have y as a function of x is equal to minus 3x squared plus 6x plus 2. And so we can see that the leading coefficient is negative, so we already know, based on that, that it looks something like this, like a frown face, right? Rather than a smiley face. Okay, so given that, let's begin by finding the set of all x such that this function is increasing. So we can see that that'll be on the left-hand side of this peak, all right, where we have a positive slope. Okay, so we need to take dy on dx, or y dash of x. So since this derivative is so easy, I'm just going to use y dash, or Newton's symbols. So y dash of x, now we bring the 2 down, and we have minus 3 times 2 is minus 6. X to the power of 2 minus 1 is x. And then differentiating 6x, we get 6. Differentiating 2, we have 0. All right, so here's our derivative. Now we want to know when y dash of x is positive. So let's write this question, or state what we're doing. Y of x is increasing whenever y dash of x is positive. But it's also of interest to find where the sign changes, or where this derivative is 0. So let's just note, all right, as a side note, y dash of x is equal to 0 when minus 6x plus 6 is 0. And if we solve this by taking minus 6x over to the right hand side by adding 6x to both sides and then dividing throughout by 6, we see that x equals 1 is the solution to y dash equals 0, and that's where this curve has a horizontal slope, or horizontal tangent. Okay, so x equals 1. Now let's immediately draw a number line so we can visualize this geometrically. So here we've got 0. Here's the right hand side of the of 0, and so on this side the numbers are positive. So where would 1 be? Let's just pick a place. 1 would be, say, there. All right, and so we have a left hand side of 1 and a right hand side of 1. All right, and this is where the sign changes. So let's say if y dash of x is positive, then minus 6x plus 6 is positive. And this is an inequality. So we can solve inequalities in the same way that we did solve equations, with a little bit of a difference. If we multiply an inequality by a negative number, then it turns the direction of the inequality around. If we invert both sides, as in a multiplicative inversion of an inequality, it also turns that around. But otherwise, it stays the same, and we can just perform algebraic operations on this. All right, and so let's do that. Let's add 6x to both sides. So adding 6x to both sides, we have 6 is greater than 6x. And then multiplying both sides by 1/6, which is positive, and so it retains the direction of the inequality. Then we get 1 is greater than x, or x is less than 1/6. Now this goes the other way too, right? We have a if then, but it also works the other way. If x is less than 1, then y dash is positive, because you can do algebraic things to this inequality and get y dash is positive. Okay, now let's visualize this. So on the left, so this is x less than 1. So on the left of 1, and let's just sort of circle that region, we have positive slope. So if I draw what that looks like this way, right? Slopes look like this on this side of 1. Now, how could you do that if you really struggle with solving inequalities? Well, you could just choose a number on the other side of the turning point, right? So we see that we have a turning point at x equals 1. If we pick something on the left of that, and so let's say alternatively, y dash of 0.5 is equal to minus 6 times 0.5 plus 6. Now, is this positive or negative? Okay, so this is minus 3 right here because that's a half of 6. So 6 minus 3 is 3, which is positive. Okay, but you have to make sure that the number that you chose is on one side or the other of the point where the slope of the tangent is horizontal, right? Okay, for this to work. All right, so from this, also we see that the slope is positive on the left-hand side of 1. All right, now let's answer the second part of this question. Find all x such that y is decreasing. Okay, and let's put an asterisk here to distinguish from the other side. So if y dash of x is negative, then minus 6x plus 6 is negative. And so again, we can add 6x to both sides. And so we get 6 is less than 6x. And then we multiply both sides by 1/6. And so we get x is greater than 1. And conversely, if x is greater than 1, then we're going to get y dash negative. Okay, so on this side we have slopes looking like this, and at 1 we have a horizontal slope. So now we have basically finished question 1, but let's write this out formally now. Okay? So formally I will write out y dash, or so let's write out x, y of x is increasing whenever x is an element of, x is in, this means is in or is an element of, the interval, so I'm going to use interval notation here, the open interval from minus infinite up to 1. And so this is not a point, this is an interval. This refers to the set of all x values on the left of 1 on the number line. Okay? Similarly, y of x is decreasing whenever x is an element of the interval from 1 to plus infinite. Okay, now I'm going to put this in a box because this is our final answer. Okay, so you can now screenshot this and write this out yourself. This completes the answer to question 1. All right, but this is going to be necessary for us to do question 4. So keep this page handy. Okay, so let's keep going and do question 2. Find any local maxima or minima. So I'm going to rewrite this. Okay, so local max or min occur when the slope is 0. Okay, so when y dash of x is equal to 0. But then once we find those, we have to classify them. Now, I've already done this on the previous page, but we'll do this again for the sake of this being a new question. So we take our first derivative, and remember we got minus 6x plus 6. Okay, so when is that 0? So this is 0 if and only if, or whenever, and I'm going to use IFF as shorthand for that. And so this, when you write this on the board, this typically means if and only if, or equivalent to whenever, or is logically equivalent to. Okay, so if and only if x is equal to 1. Now what I'm saying here is this is the unique x value that gives derivative y dash equal to 0. Right? Because this has one solution here. Okay, so it will occur here, but let's form a point now. So y of 1 is equal to minus 3 times 1 squared plus 6 times 1 plus 2. And so this is 8 minus 3, which is 5. And so then we learn the point 1, 5 is a turning point or a critical point. Okay, so now that we have that, let's classify that. And so we can classify this in two ways. The first derivative test says that if the sign of the derivative is one thing on one side of the turning point and something else on the other side of the turning point, then you have a max or a min. But in particular, if it's positive on the left and negative on the right, then you have a local maxima. All right, but the second derivative test is probably the more popular one to use. And so let's use the second derivative test here. Okay, and so we take the second derivative, so y double dash of x is equal to, now what I'm doing is just differentiating again. So the derivative of y dash, and so that is the derivative of minus 6x plus 6, and so it's clearly just minus 6. Now it's minus 6 everywhere, okay? But in particular, we want to look at what happens at the turning point. Y double dash of 1 is minus 6, and this is negative. All right, now this seems perhaps counterintuitive how to classify a negative second derivative, but what I like to do, I mean, since we know what this thing looks like, it's a frown face shape, right? What's happening? Now get your pen or pencil out and follow left to right in x values. What happens to the slope? You see here the slope being positive, and then as I go left to right, the slope is decreasing and going negative. It's decreasing, right? So when the slope is decreasing, the second derivative is negative, or the rate of change of the slope is negative. And so a negative second derivative gives us a local maxima. So the point 1, 5 is a local maxima. Okay, now we can also decide whether it's a global maxima too. Now what is the domain of the function? The domain of the function is the set of all real numbers. So domain of y as a function of x is the whole set of real numbers. Now I've written a double struck R, and this is the set of real numbers, meaning the whole number line, the real number line. Okay, so all real numbers. Okay, good. So now that we know that this is a local max, have we solved question 2? Yes, we have. This is the unique local maxima. There's no local minima. And we know it's actually a global maxima because on the entire domain, this is the top, all right? And so you can prove this algebraically as well by completing the square on that original function. So we'll say this point, 1, 5, is also a global max. Because it's the maximum of any point on the domain. All right, great. Let's move on to question 2. And again, keep this one aside because we found that 1, 5 is a global maxima. And here we know what the slopes look like. So what remains here? Well, question 3 asks us to find all values of x for which y is concave up. Okay, so y equals minus 3x squared plus 6x plus 2. Now to do this question, so concave up, I think it looks like this, right? I think that's concave up, so curving this way. But I'm not sure, so you might need to look this up. So I'm going to solve this problem. Okay, which x values, for which x values does it look like this? And we already know no x values. Okay, but let's do this with mathematics. So we already have y double dash of x equals minus 6, which is negative. And that occurs for all real x. For all x belonging to the set of real numbers. So y of x is concave up nowhere. Okay? In other words, for all x belonging to the empty set, which is the set with nothing in it. Okay, so we've done question 3, and so now question 4 asks us to sketch this. I'm just going to toss this page here on the floor because that wasn't all that helpful in sketching this. All right, so question 4 asks us to sketch this function. Okay, so I'll get my ruler out so I can do this properly, and then after I'm done, I'll get Mathematica to do the same. You can see I've got Mathematica set up to do this, but I really think we should do this by hand. Okay, so I have an x-axis here. I have a y-axis here. I know what this thing looks like, but what's missing are 3 points, or 2 points on my x-axis and 1 point on my y-axis. So let's find these. Okay, so we'll say, let's start with the y-intercept. And this occurs when x is 0. All right, so then y of 0 is equal to minus 3 times 0 squared plus 6 times 0 plus 2, which is obviously just 2. Okay, so this gives us a point. It's the point 0, 2. So let's find that point. If I say 1's there and 2's there, okay, so we have this point there. Now let's go ahead and find our x-intercepts. So x-intercepts, well, this doesn't look like it factorizes very nicely, all right? So we could have a 1 and a 2, a 3 and a 1, because 2 and 3 are both prime. But the combinations of those, no, I get 6, sorry, I get 7 or I get 5, so I don't get 6. So it doesn't have a nice factorization. So let's use the quadratic formula to find the roots of this. All right, so x-intercept, and it's plural here because we'll get multiple. So these occur when y is equal to 0. And so we need to solve minus 3x squared plus 6x plus 2 is equal to 0 for x. So let's go ahead and do that using the quadratic formula. So x is equal to negative b, so minus 6, plus or minus the square root of b squared is 36, minus 4 times a times c, and then that's all over 2 times a. Okay, let's simplify this. So inside the square root, and that is our discriminant here, we have 36 plus, because there are 2 minus signs, 12 times 2 is 24, so 36 and 24 is 60, isn't it? Okay, and then in the denominator we have minus 6. Now 60 is 4 times 15, so the square root of 60, I can express that as 2 root 15. So we have minus 6 plus or minus 2 root 15 all over minus 6. And so then we can write this as x equals, now minus 6 over minus 6 is 1. I'm going to express this as minus or plus because I'm dividing by a minus, just because it's a good habit. 2 over 6 is a third. So we've got these two numbers, right? And so you can get a quick, dirty estimate for this because 15 is close to 16. The square root of 16 is 4. So this is about 1 4/3, or approximately 2.3, right? But let's get an exact estimate here using Mathematica. Okay, so I want 1 plus 1/3 of the square root of 15. And I'm going to put a 0.0 there so I get a numerical estimate. Okay, and so we get x is 2.29 or so, and so the y coordinate is 0. And then if we put a minus there, we get minus 0.29, and also the y coordinate is 0. Okay, and so let's find these. If I put 1 there, minus 1 there, then I've got 2 here, 3 here, so about a third of the way. Okay, something like that. And then on the other side, well, minus 1/3, about, let's put it here. All right, now what we are missing is our maxima, right? And so have a look at these other pages that we have here. So we want it to look like this, but then we also got a maxima at 1,5. Now I don't know if I've left enough vertical room to put the 1,5. So you know what, I didn't, so let's redo this. That'll be 4. And so here I've got 2. And then so 5 would be here, and then 1,5 up here, right? And so we'll ignore this point. Now we've also got an axis of symmetry here, so put a dashed line under the maxima, vertically under that maxima. All right, now what we want to do is fill in the dots in a parabolic shape. It's a little tricky to do this, so just do your best. It doesn't really matter if it's perfect. All right, so I've completed question 4. So you can screenshot that if you need to. Now, let's also do this in Mathematica. Okay, so here I enter the function into memory, and all I do now is plot this. Okay, and now you can see things are not quite to scale, but if I bring this in, say from -1 to 2, it'll look more like what we have drawn by hand. All right, and so here we've got all the key features on here. I don't have the vertical line, but it's a nice, perfect sketch. Better than what I could do here. All right, let's move on to question 5, where we're going to sketch a bit of a trickier question, or trickier function. I better scroll this PDF up. So it's the same set of problems, but with a different function. Okay, so question 5. Y as a function of x is equal to x to the power of 4 minus 6x squared. And so this says find all x such that y is increasing. Find all x such that x is decreasing. All right, so in my experience, it helps to first do question 6, find the places where the sign changes. And so I want to do that first. All right, so I'm going to do this somewhat out of order. So I'm going to change this to question 6, all right? And then we'll come back and do question 5. Okay, and so now what I'm going to do is factorize this. Is that what I want to do? No, I don't want to factorize it. I want to find local max or min. All right, so let's differentiate this. So y dash of x is 4x cubed minus 12x. And then I want to factorize that. Okay, and so this is equal to, you see we have a common 4 because the greatest common divisor of 12 and 4 is 4. So I can pull a 4 out. I can also pull an x out of this. And then what would remain if I just pulled a 4 and an x out is x squared minus 3. All right, and how do I know it's this? Well, 4x cubed divided by 4x is x squared, and minus 12x divided by 4x is minus 3. All right, but I can factorize this even more because this is a difference of 2 squares. Okay, and so let's write y dash of x is equal to 4x times x plus the square root of 3 times x minus the square root of 3. All right, and so now what we have is a fully factorized form of the first derivative, which tells us by the roots of these 3 linear factors where we have a horizontal tangent or a turning point. Okay, so turning occurs when y dash of x equals 0. So in this case, the 3 roots of this, x equals 0, or x is equal to minus root 3, makes this one 0, or x is equal to plus root 3, which makes this one 0. Now root 3 is about 1.7 or so, all right? So we haven't fully done question 6 yet because we've just found where maxima or minima should occur. Now let's classify these. We classify this by taking a second derivative. So I'm going to use the second derivative test here. So second derivative test, abbreviating that, y double dash of x, and so I'm just going to differentiate this unfactorized form again. So the 3 comes down, so we have 4 times 3 is 12, x squared minus 12. All right, and so it might help to have a factorized form of this also, so I can pull a 12 out, and then what remains is x squared minus 1, but I can factorize that as x plus 1 times x minus 1. Okay, so here's our second derivative. Now, the second derivative test says when the second derivative at a given point is a particular sign, then we can judge whether it's a max or a min. All right, so let's sub these in. So y double dash of 0 is equal to, just looking at this, that's minus 12, and that's negative. Okay, so when we have a negative second derivative, we have y dash decreasing. And so let's just draw a picture for this. It's like this, okay? Frown face shape. All right, so the point 0, now what is y? It's 0 in this case. So 0, 0 is a local maxima. Local max for short. Now let's evaluate at the next point. So y double dash of minus root 3 is equal to, all right, so if I just take this form of y double dash, minus root 3 squared is plus 3. So we've got 12 times minus root 3 squared and then minus 12. So this is 12 times 3 and then minus 12. And so that is 36 minus 12, which is 24. And that's positive. And so let's find a corresponding point. Minus root 3. What is the y value? Well, if I square minus root 3, I get 3. And so now the fourth power is the squared squared. And so we have 3 squared is 9. So 9 minus 6 times 3. And this is minus root 3. And so that's 9 minus 18 is minus 9. So this point is a local minima because we have the slope increasing. Okay, so we found a local max and a local min. Now, on the other side, when x is plus root 3, well, the calculations are the same because these get squared, right? And so we have, what do we have? We have 24 again. And that's positive. So root 3 minus 9 is a local minima. Okay, so we have local max and 2 local minima. Now let's place these geometrically here in what might be a bad sketch. All right, so here we've got our origin, and we found out that that was local max. Okay, and then at about 1.7, so say here we have a local min, and on the other side, symmetric about the y-axis, we have another local min. All right, so far we've learned that it looks something like this. Now what's missing to be able to sketch this is intercept points, or x-intercept points, because we have a y-intercept point. Okay, and so we would want to factorize this equation right here, but let's factorize it now. Okay, so we can pull out a common x squared. Then what remains is x squared minus 6, and so we can factorize this even more. So x squared, x plus root 6, x minus root 6. Okay, and so that tells us that the x-intercepts occur at 0 and plus or minus root 6. So we only have 3 distinct x-intercept points. Now the square root of 6, where is this? 6 is less than 9, so the square root is less than 3, but 6 is greater than 4, so it's more than 2. Okay, so let's put it somewhere in here. And so this will be a rough sketch of this thing. Connecting these up. So it's going to look something like this. So we've kind of already done question 8 here. All right, and so I'm going to label this question 8. All right, so we found any local max or min, so we've done question 6. Now I'm going to save question 5 till the last because that's arguably the more difficult one to do. Question 7, find all values for which x is concave up. Okay, well that's a separate one. Let's do that next on another page, but we'll keep this page handy. So question 7. So we've got y of x is x to the 4th minus 6x squared, and we're looking for concave up. And so again, I'm going to assume that that looks like this. All right, so where is the second derivative positive so that the slope would be increasing? Okay, now what was our second derivative? Well, we got y double dash of x equal to 12x squared minus 12, which we found to be equal to 12 times x plus 1, x minus 1. Okay, so we need to separate. We know where things change. Things change in sign here at both plus 1 and at minus 1. Okay, so let's find this. 0, 1, minus 1. All right, so let's say then if x is greater than 1, then this would be positive, and this would be positive, and so y double dash of x would be positive. All right, and now if x is between minus 1 and 1, so in here, then y double dash of x, okay, now just choose a number between minus 1 and 1, say 0. If we sub 0 into this, or even 0 into this, we've got something negative. So that'll be the general case there. This second derivative will be negative in this region. All right, and you can see this from our sketch too, because the slope will be decreasing there. All right, and so where is 1? Let's fill that in with a dash line. So within this region, we've got concave down. And so let's say in brackets, concave down. Okay, and then in our third case, on the left-hand side of minus 1, so if x is less than minus 1, now again, we can choose a number to think about this and sub it in here. So say if we sub in minus 2, okay, 12 times minus 2 squared is 12 times 4 is 48, minus 12, that's 36. That's a positive number. So y double dash of x will be positive there. And we can see that here. On the left-hand side, we have concave up until we get to 1. Okay, and so all of those pieces together should help us sketch this, right? But we've missed question 5. Okay, and now question 5, I said it was a little bit tricky. It's helpful to know the roots of the first derivative, so let's go ahead and find that again. So we know the roots of the first derivative are 0, minus root 3, and plus root 3. Okay, so let's take some of the information we have from question 6 to do question 5. So we have y dash of x is equal to 4x times x plus root 3 times x minus root 3. All right, now what I want to do here is draw a number line and identify the three roots. So 0, and we've got 1, we've got 2, and then plus root 3 would be about 1.7. So let's label it there. And then on the other side, we've got 1, we've got 2, and then minus 1.7 or so, we've got minus root 3. All right, so let's fill that in. Fill that in here as well. And then let's identify 0. So what are my regions? So regions of interest here are on the right-hand side of root 3. And then we have a region between 0 and root 3. We have a region between minus root 3 and 0. And we have a region on the left. Okay, so let's label these region 1. Then we have a region 2 of the number line. And we have a region 3, and then we have a region 4. All right, and so let's determine the sign for all x in region 1. So if x is less than minus root 3, then, well, x will be negative, so this will be negative. What about this? This will be positive. Is it? No, this will be negative. And this will be negative. But if you're really unsure, because it's a little bit tricky to think about the logic there, you can choose a number that is less than minus root 3. Okay, so let's just choose one. What about if we just choose y dash of minus 2 as a representative for what happens in that region? Okay, then we would have minus 8, and then we would have minus 2 plus root 3, and then we would have minus 2 minus root 3. Okay, so negative, negative, negative. Okay, and so that product would be the product of three negatives, which is negative. So we would have a negative slope there. All right, so let's make a line with a negative slope. All right, now what about in region 2? Okay, so let's say if x is greater than minus root 3, but less than 0, so x is negative, but it's greater than minus root 3. So can you think of a number in that range? So y dash of, say, minus 1 is equal to minus 4. I'm just subbing that number into this. Minus 1 plus root 3. And then over here, minus 1 minus root 3. Okay, so this time, this is negative, this is positive, this is negative. And so we have two negative numbers times a positive number. That's positive. And so in region 2, we have a positive slope. Now in region 3, we're going to get a negative slope. So we'll say if x is greater than 0, but less than root 3, then we see that just subbing in a number, so let's take 1. So y dash of 1 is equal to 4 times 1, and we have 1 plus root 3, and then we have 1 minus root 3. Okay, so positive, positive, negative, and so the result is negative. So we have a negative slope in there. Let's identify that with a negative line segment. All right, so if x is greater than root 3, well then in this case, let's choose a number that's greater than root 3, say 2. So y dash of 2 is 4 times 2, Then we have 2 plus root 3, and then we have 2 minus root 3. Now this is positive, okay? And so in this region, y dash of x would be positive, and so we get a positive slope in that region. All right, now let's answer the question properly. So to answer the question properly, where or which x values do we have a positive slope? Okay, and so it'll be the union of these two regions. So we'll say y dash of x is positive whenever x is an element of the interval from minus root 3 to 0, but there's another interval as well, so we'll use a union symbol. And so this means we're gluing together the sets, x is in this or x is in this set. And so on the other side over here, this is root 3 to infinite round bracket, because we don't include those endpoints themselves. Okay, and so y dash of x is negative or decreasing whenever x is in this region or, this region or this region, region 1 or region 3. And so that would be minus infinite up to minus root 3, union 0 up to root 3. Okay, and so that answers question 5. So piecing all of this together, your screenshot is a little bit trickier to do. So, you know, maybe something like that, but there's a bit more here. Okay, let's move on now to question 10. Except for I want to do a Mathematica plot here, so I'll just press the button so you can see this. All right, so this is what Mathematica plots, and so that would answer question 8 using Mathematica, but you know, this was a by hand question. All right, so let's move on. So next we're going to do question number 9. So in question 9 we have a quadratic function, and it says sketch this. All right, and so to sketch this, we know what this looks like. Its leading coefficient is positive, so it's like a smiley face rather than a frown face. Hang on, that's minus 20. Okay, so 4 is positive, so we have smiley face, right? But let's fill in some more details. All right, so first, y of 0 is, subbing 0 in here, we have minus 20. So we have a point 0 minus 20. All right, now next, where is y equal 0? Y is equal to 0 if 4x squared minus 16x minus 20 is equal to 0. Now we want to factorize this. We can see that each of these is divisible by 4. So let's factorize a 4 out. So 4 outside of x squared minus 4x minus 5 equals 0. And so we see we need to factorize this quadratic here inside the brackets. That's easy to do because 5 is 1 times 5 and the difference is 4. So we have 4, put an x, put a 1, put an x, put a 5. Okay, let's determine the sign of each of these inside the brackets. Now, this is negative here, so we want one of these to be positive and the other negative, but their difference is negative, so I want the larger number to carry the minus sign and the smaller to carry the plus sign. All right, and so this gives us x is equal to minus 1 or x is equal to plus 5. Okay, and so this gives us 2 points, minus 1, 0, and 5, 0. All right, and so now we have 3 points on the axes. So at this point, you might want to start sketching. Let's find these. We've got to accommodate minus 20, so we can't exactly do this to scale. So let's put minus 20 down here. And this would be minus 10. And this is the origin 0, 0. Okay, now we can do a different scaling on the x-axis. So -1, let's put that there. Then 2, 3, 4, no, that's 3, 4, 5. Okay, so 5 would be here. All right, now this is smiley face, so we've got something like this and passing through here. Now we need to know where the bottom is so that we can sketch this properly. All right, so y dash of x is equal to 8x minus 16. Now where is this equal to 0? Okay, let's solve this equation right here. Well, clearly we take the 16 over to the right-hand side and divide by 8, and we get x is equal to 2. And when x is equal to 2, what's the y value? All right, so I'll use the factorized form. So y of 2 is equal to 2 times 2 plus 1 is 3, subbing in there. And then 2 minus 5 is minus 3. And so I've got 4 times minus 9 is minus 36. So that gives us a 0.2 minus 36. Okay, so let's find this on our graph. So minus 30. Then down here we might have minus 40. So 36 might be around here, right? So let's draw a dotted line over. Now this happens when x is 2. So round about here, right? Okay, and so we know that this is smiley face shape. So let's fill in our parabola. And so we have something like this. All right, so there we did that by hand. All right, so you can screenshot that. Now I'm going to go to Mathematica and plot this. And so this is what Mathematica gives us there on the left. All right, so we've now done question 9. So let's move on to question 10, where we've got to sketch a cubic. So y equals 4x squared, no. Y equals x cubed minus 9x squared plus 15x plus 1. Okay, so what we can find here is we can find a y-intercept. So let's notice y of 0 is equal to 1. So we have a point 0, 1. Now we cannot easily do the same thing for the x-intercepts. I mean, we can, but we have to do this numerically. All right, so I'm just going to get on a machine and show you that it's kind of annoying. All right, so I'll say numerically solve this for x. All right, and so we have 3 other points that we got using a machine. And so not so easy to use to do this by hand. You would need Cardano's formula. So by machine, we've got minus 0.0640. Then we have 2.31, say 0. And then we have 6.76, 0. All right. So these are our x-intercepts there. So now how do we want to actually sketch this? And you can see I've got Mathematica to sketch this for us. So that's a classic cubic shape there with positive leading coefficient, or a positive cubic. Okay, but I've got to do this by hand. So what do I want to do? I want to find out where my turning points are. Okay, so I take a first derivative. Y dash of x is equal to 3x squared minus 9 times 2 is 18x, and then plus 15. Well, this is nice because clearly each of these terms is divisible by 3. So let's factor out a 3. So y dash of x is equal to 3 outside of x squared minus 6x plus 5. And how do I know that? Well, I see each of these is divisible by 3, and so then I divide them by 3. 3 divided by 3 is 1. 18 divided by 3 is 6, but I carry the minus sign there. 15 divided by 3 is 5. Now this is clearly easy to factorize because 5 times 1 is 5, and the sum is 6. And so we have 3 outside of x with a 1, x with a 5, but the product is positive, so these should have the same sign. That sign should be minus because the sum of those is negative. Okay, so we're able to factorize the first derivative easily, even though it's not as easy to find these intercept points. All right, and so the roots of these, so we'll say when y dash of x equals 0, we have x is equal to 1, or x is equal to 5. Okay, and so let's find this on the number line because, so this gives us points, but we would have to sub the 1 and the 5 in here to get the points, right? Okay, but let's identify on the number line. So if 0's here, we might have 1 here, and then 2, 3, 4, 5 over here. Now, if I pick a number that is less than 1, say 0, and sub it into this, I've got 15, which is positive. Okay, so positive slopes on this side. Now pick a number between 1 and 5. Okay, say 2. So if I sub 2 into this, then 3 times 2 minus 1 is 1, so this part is positive. 2 minus 5 is negative, so I get a negative slope for numbers in between 1 and 5. Okay, so something like that. Now if I choose a number that is greater than 5, say 6, sub it into here. So I have 3 times 5 times 1, that's positive, and so on this side I have positive slopes. All right, and so that's how we know it has this classic positive cubic shape. Much like what you see in the plot by Mathematica there. All right, so we know those points. Now, we know where it's positive and negative. Okay, but what about finding these as actual points? Because that would be useful too, into getting a proper sketch by hand. So, y of 1 is equal to 1 cubed minus 9 times 1 squared plus 15 times 1 plus 1, and this is equal to 1 minus 9 plus 15 plus 1. Now 15 minus 9 is 6. 6 plus 1 is 8. So we have a point which is a turning point, the point 1, 8. Okay, let's do the same thing for 5. So y of 5 is 5 cubed minus 9 times 25 plus 15 times 5 is 50 plus 25 is 75, and then plus 1. All right, so 5 cubed is 25 times 5, which is 125. And then 8 times 25 is 200, so this will be minus 225. And then we have plus 75 plus 1. Okay, so I'm doing mental arithmetic here. So this part of it will be minus 100. So 75 minus 100 is minus 25. We have 1 minus 25, which is minus 24. So this gives us the point 5 minus 24. Okay, and so now we have all the ingredients we need to sketch this. So let's make a go of sketching this. Okay, and so we have the point 0, 1. Let's put that there. Then when x is 1, we have y is 8. So let's put that, say, up there. And then when x is 5, Say over here we've got minus 24, so that would be, say, way down here. And then we kind of know what this looks like, right? And then it just keeps increasing. Okay, and so much like what we have there on the left of my screen in Mathematica. All right, so let's move on to question 11, where we've got to sketch a quintic. Okay, in question 11, we are asked to sketch x to the power of 5 minus 20x squared. So, is this easy to factorize? Yes, it looks like it is relatively easy to factorize. I can factorize a common x squared out. Then what remains is x to the power of 3 minus 20. Okay, now this has 3 complex roots, but only one of those is real. So I know that I'm going to get the cube root of 20 as one of the real roots. So we have 3 real roots. One of these is repeated. So x equals 0 is a repeated root. And so we have 2 distinct real roots at x equals 0 and x equals the cube root of 20. Okay, let's get Mathematica to estimate what that is. So numerical estimate for 20 to the power of 1/3. Okay, 2.714. So that gives us 2 approximate points. So we've got 0, 0, or approximately 2.714, okay? So these are our 2 x-intercepts. Okay, so given that, let's move on to find, are there any y-intercepts? Yes, there is, because when x is 0, we have y is 0, so this is a y-intercept also, and it's the only y-intercept. So under that, let's say only y-intercept. Okay, abbreviated. All right, so let's start sketching this with what we have. So here's 0, 0, and then 2.74. So let's put 1, 2, 3. So somewhere in here. All right, so these are our 2 x-intercepts. All right, now let's seek other features. So y dash of x is equal to 5x to the power of 4 minus 2 times 20 is 40x. Okay, can we factorize this? Yes, they're both divisible by 5, and we can pull out a common x. So y dash of x is equal to 5x outside of x cubed minus 8. Okay, and we can see that this has 1 real root. It has the one unique real root 2. So the roots of this are x equals 0 and x equals 2, the real cube root of 8. All right, so let's identify this. So 2, that's here. All right, can I sub this in there and get a number? So y of 2 is equal to, so 2 squared is 4, and then we have 8 minus 20 is minus 12, right? Yeah. 8 minus 20 is minus 12, so minus 12 times 4 is minus 48. And so what we've learned then is that the point 2 minus 48 is a turning point. So it has y dash equals 0. And then the other one, 0, 0, also has y dash equals 0. Okay, so let's identify this other one on our graph. So if I put minus 10, minus 20, minus 30, minus 40, minus 50, so that would be down here. Okay, so we have a lot of key features. Now, let's take a second derivative. So y double dash of x, now differentiating our first derivative, we bring the 4 down. So we have 20 x to the power of 3 minus 40. Okay, so y double dash of 0 is minus 40, which is negative. Okay, so what's happening? Our slope is decreasing there, and so we learn then that this is a local maxima. All right, so let's do the same thing with 2. Y double dash of 2. So 20 times 8 is 160, and then minus 40 is 120. That's positive, so we get a local max there, and so let's fill that in like this. And then we know that it crosses at about 2.7. So the sketch should look something like what I'm drawing here. All right, let's get Mathematica to sketch this as well. Yes, and it looks a lot like a cubic, and so, you know, it's a bit flatter here, right? More change on this side. All right, let's move on to question 12. Now in question 12, you see I've chosen a function. So let's just run this. Okay, so I've chosen the natural log of x, which has all of these features. So we've got a function that satisfies these properties. F of 1 is 0. F dash of x is positive for all x in our domain. F double dash of x is negative for all x in our domain. All right, but the domain of the natural logarithm function is the set of all positive numbers. So note, f of x is equal to natural log, and I'll write ln for that, satisfies f of 1 is ln of 1, but notice e to the power of 0 is 1, so it does satisfy this. Ln of 1 is 0. Okay, so we satisfy that first property. F dash of x, if we differentiate the natural log, we have 1 on x, and if x is positive, then this is positive. So this is positive for all x greater than 0. Okay, now let's take the second derivative. So f double dash of x is equal to the derivative of x to the minus 1. So I bring the minus 1 down, and we have minus x to the minus 2. And so we can write this, f double dash of x is minus 1 on x squared. And so this is negative for all positive x. So it satisfies all of these. Okay, now, so a function that has positive slope, right, follow the pen there, something like this, but the concavity is such that that slope is getting less and less and less, right? The rate of change of the slope is negative. And so we have something like this. So you could take these three criterion and draw this without knowing that it should be natural log. And I think that's what you're meant to do here in this question. All right, let's have a look at question 13. Question 13 asks us to sketch a continuous curve such that f of 0 is 2, f dash of x is positive for all x in the domain, second derivative is negative for all x in the domain, and then the third one, we can write this as the limit as x approaches infinite of f of x is equal to 4. All right, so let's have a look for such a function. So if I start to try to sketch this, when x is 0, we have 2. So we got a point there. It has a positive slope, so something like this then, but it's curving a lot like the logarithm function did. And then, but this last one says that it tops out. It has a maximum at 4. So if I do that, I want to put a horizontal line here. And so it looks something like maybe this, where it has a maximum of 4. Is there such a function? Well, yes, there is. So let f of x be equal to, let's see, 4 minus 2 over the square root of x plus 1, say. Okay, now let's take the derivative of this. All right, now to do this, you would use the chain rule on this one, or you could even use the quotient rule. And so f dash of x is equal to the derivative of 4, which gives 0, and then we have minus 2 times the derivative with respect to x of x plus 1 to the power of minus a half. Right, so this requires the chain rule. So we say then that this is minus 2 times the derivative of x plus 1 to the minus a half with respect to x plus 1. And so if you're setting things out, then this x plus 1 would be the u, and then times du on dx. So something like this. Right, now if this is my u, what I have then is the derivative of u to the minus a half with respect to u times dx plus 1 with respect to x. Now this derivative is just 1. To do this one, we bring down the minus a half. So we have minus 2 times minus a half, and then we subtract 1 from the exponent, so we get u to the power of minus a half minus another 1, which is minus 3 over 2, and then this derivative here is 1. Okay, so if I simplify this, I've got f dash of x is equal to, the product of these two is just plus 1, so u to the minus 3 halves is our derivative there, but this is x plus 1 to the minus 3 halves, which you can write as 1 over the square root of x plus 1 to the power of 3. And then you can even pull out an x plus 1 squared, which when you square root that becomes x plus 1. So we get this as f dash of x. All right, and so you can see that it has the right features. So for x greater than 1, inside the square root is positive, this is positive, so this is positive for x greater than 1. Okay, now if you differentiate that again, well, you're going to need the chain rule again, and you're going to get minus 3 halves x plus 1 to the power of minus 5 on 2. All right, and so that, because a minus comes down, it has this property that it is negative. Okay, let's move on to question 14. So now we begin to do some optimization. We're finding maxima and minima subject to a constraint, but we're going to do this without Lagrange multipliers. We're just going to do this with basic calculus. So in question 14, what you want to do here is draw yourself a picture. Okay, so here is a rectangular corral, and in here you might draw yourself a horse. Okay, so there's my horse. All right, and so let's call the width of this x, and the width of this side, let's call that y. All right, now we are told that x plus y, because we have these on both sides, right? Remember, this is a rectangle. So the perimeter of this is 2x plus 2y, and it all adds up to 2400. Now this is our constraint, right? But you can see that everything there is divisible by 2, so we can simplify and write this as x plus y is 1200. And then if we want to write y as a function of x, we can do that here. That's easy. So y is equal to 1200 minus x. All right, so we've rewritten our condition for the perimeter. Now what about the area? So this asks us to find the maximum possible area of the corral. So the area is equal to x times y. Now we have a rearrangement for y there. So area as a function of x is equal to x times 1200 minus x. Okay, now just to make this easy, we can expand this and say 1200x minus x squared. So now we want to find the maxima, right? Now if we were to just do a rough sketch of this, it has a leading negative coefficient, so it looks something like this if we plot this function. X on the x-axis and a on the y-axis. So at some point there's a maxima here, right? Just because we know what this looks like already. All right, now to find that, so to find the maxima, we calculate a dash of x, and so we differentiate this function and we get minus 2x plus 1200, or 1200 minus 2x. All right, so where is this equal to 0? So a dash of x equals 0 whenever we have minus 2x plus 1200 equals 0. Okay, and so we can easily solve this. So we solve this by taking the 2x over to the right-hand side, and then I'll swap sides. So we get this, and now we want to divide by 2 and get x is equal to 1200 over 2, which is 600. Okay, so this is a turning point. Now, just to verify that this is a local max, let's take the second derivative, and so we'll do the second derivative test. So the second derivative here, just differentiating this again, we get minus 2, and that is negative. So a double dash of 600 is negative, right? And so we learn that we have a local max. So the point 600 something is a local max. All right, now we know that. Let's find the actual y value. So A of 600 is equal to, so let's look at this. So we have 600 times 1200 minus 600. Right, and so that's 600 in the bracket. So this is 600 squared. So 6 times 6 is 36. And then 100 squared is 10,000. So we have 360,000 there. Okay, so let's put this in here. 360,000. I'll even put a comma there to make it easier to read. All right, now it's also a global max because what is the domain of our function? So domain of the function here, considering the parameters of the problem, x has to be positive because it's a side length, and y has to be positive as well. So the maximum x could go, given that constraint, is 1200. All right, so. But let's put a round bracket so we don't include the extremes. Domain is the interval from 0 to 1200. Okay, now to determine the global maximum, we compare the values within the domain against the extremes of the domain. And so we can see clearly that this is the global maximum. So 636 or 360,000 is a global maxima also. All right, so now that we've got this, so you can screenshot this if you like. Now let's go to Mathematica and get a visualization on this, question 14. So the first plot that I have is just using the manipulate command to draw us a little rectangle. And I think I want to make this smaller so it fits nicely. But can I do that? Okay, so what this allows me to do is change the size of my rectangle, so I can imagine this. So what happens when I change the rectangle? But this neglects the constraint. So if I include in my graphics the constraint, and you know, I think I'll just drag this down rather than resize that. Okay, so if I use this in here, this constraint, now I'm manipulating this over only one letter. Right, so what I'm displaying here is the x value here. I'm displaying the area. I'm showing the rectangle, but the blue line that you see here is just the line of that constraint. And so the x and y point at the opposite end follows that constraint in our geometric diagram here. So let's see what happens to the area. That area increases until I get to a certain point, right? So it's maximum here when this rectangle is a square, but then as I keep going, I get up to 360,000, but then it goes down again once I start to have another non-square, right? All right, now in light pink shown is the actual parabola that I've drawn here. Right, and so you can see that that reaches its maximum when x is 600 and the area is 360,000. All right, so let's move on now to the next question. Question number 15. And I'll bring this back. And have a look at question 15. And by the way, these questions come from a text by Washington. I think the name might be Calculus. All right, a small oil refinery estimates that its daily profit in dollars from refining X barrels of oil is P, which of course is a function of X, is 8X minus 0.02 X squared. How many barrels should be refined for a maximum daily profit, and what is that maximum daily profit? Let's do a quick rough sketch. Looks something like this. Leading coefficient of this parabola is negative, so it has a maximum and looks like a frown face. So to do this, we need to take the first derivative, p dash of x is equal to 8, and bring the 2 down, so we have minus 0.04 x. So when is this 0? We want to solve this equation for x. Okay, so we take the minus 4x, minus 0.04x to the right-hand side. So we have this. Now we want to divide both sides by 0.04, but I'm going to do some mental arithmetic, so let's express this as 4 over 100. So 4 over 100. Okay, but can we simplify this any? Well, there's no real need to, because I want to divide both sides by that 4 over 100. So x is equal to 800 divided by 4, which is equal to 400 divided by 2, or 200. Okay? Now, this is the only root of this linear equation here, right? And so this is our axis of symmetry, but then over here we've got the y-axis. So this occurs at 400. Sorry, at 200, isn't it? At 200. All right, so next, let's confirm this is a local maxima by taking the second derivative and applying the second derivative test. So the second derivative is the derivative of this, which is minus 0.04, and that's negative, and it's negative at 200 as well. Okay, so this is a local maximum, but it's also a global maxima because our domain is positive barrels of oil, so x is greater than 0. And then we would want to go up until we meet the axis again, where this profit becomes negative. So the point 200, comma, now what is this when x is 200? It's p of 200. So P of 200 is equal to 8 times 200 minus 2 over 100 times, because 0.02 is 2 over 100. And so then if I multiply that by 200 squared, okay, let's simplify this. So we have 1600 minus, so this is 2 times 4 times 100. So we're subtracting 800 from that, and so we have a maximum profit of 800. So there, our point is 200, 800. Okay, and that answers that question 15. So let's go ahead and move on to question 16. All right, so let's do the Mathematica on that as well. So Mathematica gives us the same thing. Okay, question 16. The sum of the length, L, so we've got a rectangle again, L and W. So L plus W is equal to 280 centimeters. So this then gives us that L, I guess L is probably a better letter to get rid of. So L is equal to 280 minus W. Now we're asked to find the maximum area. So A is equal to L times W, which is W times 280 minus W, which is 280 W minus W squared. Okay, taking the first derivative of A as a function of W, we have 280 minus 2 w, and we're seeking where is that 0. So we want to solve this equation. So we're solving 2 times w is 280. So I divide both sides by 2, and I have w is 140. Okay, so we found where this occurs, where our maximum occurs. In the area function. Now, what is the maximum area? So I take that 140, I sub it into the expression for A, and we have 140 multiplied by 280 minus 140. And so we have 140 squared. So 14 squared is 96, so 96, and then 10 squared is 100. So 9,600 centimeters squared. Okay, so here I've got I'll just plot this. You can see that this is a maximum occurring when W is 140. All right, let's move on to question 17. All right, 17 says we've got a rectangular animal display, but in there's a partition. What dimensions give the maximum area for the display if a total of 120 meters of fencing is used? Again, let's label this distance y, and this distance across here, let's label that x. All right, so 120 is equal to x plus x, or 2x. And then we have 3 segments of the y, so 3y equals 120. All right, this is our constraint. Now we want to solve this constraint for y. So we subtract 2x from both sides and write 3y equals 120 minus 2x, and then we divide that throughout by 3. So y is 1/3 of 120 minus 2x. Okay, now, what dimensions give maximum area? So the area of this is equal to x times y, but given that y is this, we have 1/3 of x times 120 minus 2x. Now let's expand this because it'll be easier to differentiate. So when we expand this, 120 divided by 3 is 40. So then 40x, and then minus 2/3 x squared. Okay, so there's the expansion of a, and it's now a function of x. So differentiating this, a dash of x is 40 minus 4 over 3 times x. When is this 0? Well, it's 0 when x is equal to, so taking the 4/3 x over to the right hand side and then dividing by that, so we get 3/4 times 40, and so this is 30. So when x is equal to 30, now what is the corresponding y value? Well, just sub it into the constraint. Y would be equal to 1/3 of 120 minus 2 times 30 is 60. So we have 1/3 of 60, which is 20. All right, so what dimensions? So dimensions, x is 30 and y is 20. All right, next question, and that's the last one for now. Question 18. What's the minimum slope of y equals x to the 5th minus 10x squared? Okay, so what is the slope? So slope is equal to y dash of x, which is 5x to the 4th minus 20x. Okay, and so let's rename this so it doesn't get confusing. S as a function of x is 5x to the 4th minus 20x. All right, so we want to find the minimum value of s. So we take the first derivative of s, which is the second derivative of y. And so we get 5 times 4 is 20, x cubed minus 20, and we can even factorize this as 20 out of outside of x cubed minus 1. All right, now where do we get 0 in this? The only real solution to this is when x is equal to 1. So unique real root when x is equal to 1. So what is the minimum slope? Well, we need to calculate what is s of 1. S of 1 is 5 times 1 to the power of 4 minus 20 times 1. And so this is 5 minus 20, which is minus 15. All right, so let's now plot this with Mathematica and wrap it up. So what I've plotted here is the original function y of x in blue. All right, that's a quintic. And then I've plotted in orangey yellow, more like mustard, right? I've plotted the slope function, which is s of x. All right, and so you can see that that does have a minimum here when x is equal to 1. So right here, and the y value is minus 15. So, you know, that looks about right. Okay, that's it for now. Thank you.